Good afternoon, Harshvardhan. Am I clear? Am I audible?
Yes, sir. Good afternoon, sir.
A slide is visible. Slide is visible, Harshvardhan.
Yes, sir.
I've sent your marks, quiz 2 marks. Have you got it?
Yes, sir. We received it, sir, in this morning.
Okay. So last times we are discussing the photo detector noises. I started these ones. We have discussed it. Harshvardhan, we have discussed these things.
Sir, last class I couldn't come, sir, because of some health emergency, sir. So I don't
So
know.
anybody who is present? Okay. Anyway, let us start with these things. Detector response. I mean, photo detector noises. Earlier we have discussed the pin photodiode and avalanche photodiode. Because you see, these things are to be covered quickly because in the March itself, one more quiz, third quiz after Holi, maybe or next. That is that week. That week it is March 18. Either maybe 24, 25 within this March again we have to conduct that week after Holi. Next week third quiz will be conducted, right? So we have to finish quickly. So here you see in the photo detectors we have seen the two types of photo detectors: pin photo detectors and avalanche photo detectors. In pin photo detectors we have discussed that there are three layers are there: P layers, intrinsic regions, and N layers are there. And when the output power is sufficient at the output end of the fiber, power is moderate, that times you can use pin photodiode. But when the signal is very weak, say for single mode fiber, that times you have to use the avalanche photodiode, where because of its avalanche effect, Kerr multiplication results, and we can have some internal gains. So we have seen these last times the pin photodetector principles and avalanche photodetector principles. Also, we have seen these two the important parameters of pin and APD photodetectors, like responsivity, quantum efficiency, responsivity, response speed. These factors are most important while considering the photodetectors. These are to be taken into account while designing the photo or while choosing the photodetectors for particular applications. Well, when you use these photodetectors, also you have to consider the noises, photodetector noises, and because last time we have seen this. After photodetector, actually current is very small. This current is to be amplified, and when these photodetectors are used in fiber optic communication systems, particular signal to noise ratio. I mean, photodetectors and its circuit should be chosen in such a way that a particular signal to noise ratio is maintained. And in that context, we have seen signal to noise ratio. That is, we have seen last times. Signal to noise ratio, that is the ratio of the signal power per photocurrent. Just a minute. S by N. Okay. Just a minute. Wait, I'm just connecting the tab. So last time we have seen this signal to noise ratio, that is actually signal power from photocurrent divided by the photodetector noises plus amplifier noises, right? Because you have to amplify after photodetector current is very small, you have to amplify. So but when you do the amplifications, some noises are involved, have to be considered, right? So amplifier noise would be there. So to get to maximize the signal to noise ratio, you have to increase the signal power, or also or you can reduce. If the signal power is constant, then you have to reduce the photodetector noises and amplifier noises. So the two parameters are there where you can increase the signal to noise ratio. And also in this context, I told you sensitivity. There is a minimum detectable power corresponds to signal to noise ratio equal to 1, right? So that is the sensitivity that is also used. So to consider these noises, so we have we should have a thorough knowledge what are the different types of noises that must be considered while performing the analysis of signal to noise ratio. In that context, okay, we have seen it last time. So this circuit we have considered. So you have modulated, modulated photocurrent incident. I mean, say this is the photodetector. This is the photodiode capacitance. This is the diode resistance and equivalent circuit. Last time I have shown it. Just a quick review. Simplified models, and if you consider the equivalent circuit of the receiver, photodetector receiver, then this is the photodiode capacitance. This is the diode resistance. Next, there will be a load resistance. Next, there will be amplifier resistance and amplifier capacitance. So these are to be there. The simple model is there. Generally, this is very small, so it is neglected. Maybe few ohms. RL, of course, large, quite large, maybe kilo ohms. So amplifier resistance capacitance will be there. So total resistance will parallel of these two. This is load resistance. This is amplifier resistance. This is the amplifier capacitance, CA. This is CD. So in this way, you can calculate the total capacitance, total resistance in the receiver circuit. So when the light falls on the photodetectors, you see, you can calculate the photocurrent that is generated IP H T at certain instant T. That will be eta Q upon H nu, eta Q upon H nu times P power falling on the device photodetectors. Right, eta Q upon H nu times because that is the definition of efficiency. IP by Q divided by P by H nu. That is the number of carriers generated by number of photons incident. Right. So from this you can find out this photocurrent, and this photocurrent consists of the two components: signal component and the DC component. Right. And mean square signal component, that is for pin photodiode, that is IT square average, that is you see IP square T. That is for pin photodetectors. And if the signal component is IP, the mean square signal component for pin photodiode will be same as this, but for this is ISS square, the signal component. And so, but for this is for pin, and for APD photodetector, gain factor will be there, because we have seen it. Responsivity is M times the responsivity that is for pin photodiode. Gain factor will be there M, right? And this M actually M for pin photoroid, that is IM by IP. These are most important relations. Numerical problems might comes. This is a multiplied photocurrent divided by unmultiplied photocurrent for pin photoroid, just like pin photoroid. This is actual output that you can have it from avalanche photodiode. So that is a gain factor. So gain factor will be there. Otherwise, other things in this one, signal component. So that is this once this difference will be there, and you can calculate this signal component. If you know the modulation index, IP can be calculated m square by 2 by times IP square. So these are the things that there, right? This is the signal component. Now the noises you see in the photoreactor, when you consider the noises, there are several kinds of noises are there. You see quantum noise, dark current noise, thermal noise. Quantum noise, that is because of the statistical process of the quantum detection process. Right. So because of the statistical nature, there will be some fluctuation average over some DC value. Right. This is a DC value IP. So quantum noise current, mean square quantum noise current, it is proportional to the bandwidth photocurrent, average value of the photocurrent. And also it depends on the bandwidth of the photoreactor. So IQ square, that is twice IP B Q M square FM. These factors are included because of the avalanche photodiode. But if it is pin photodiode, then M will be equal to 1, FM will be equal to 1. This FM actually is a noise figure. FM equal to, you see it here, M to the power X, where X can vary between 0 to 1. X can vary, right? So the noise figure. So these factors will be 1 for a pin photodiode. So 2 IPBQ M square FM, that is the mean square quantum noise current, right? So the region quantum noise current is because you see if 5 photons incident on the device, not necessarily 5 electron hole pairs will be created all the times. Can be 4, can be 3, like this thing. So some fluctuations will be there. So that is actually the quantum noise current. So next is the dark current noise. Dark current noise can be 2 types. Can be bulk dark current noise, can be surface leakage current noise. Bulk dark current noise, that is because of thermally generated carriers, and it will have some average value ID. This is the average dark current. So mean square dark current noise, that is 2Q ID times B times M square FM. Here also average factor is included because it's a bulk process, right? Avalanche effect is a bulk process. So here also we have to include these factors AM and FMs, right? But for pin, this will be 1. Next is surface leakage current. In case of say that is the surface leakage current, this will be present for pin and both pin APD, and here you see that is because of surface, because of defects, cleanliness, supply voltage variation, etc. For these things, surface leakage current will be there. Of course, that can be minimized by special some ring structure, just like eddy current I told last time I discussed. So eddy current, like this eddy current, so it can be filtered out using some ring special structure, right? Surface leakage current. So that is actually 2Q IL into VIL, the average value on this surface leakage current. So here M square FM is not, because it occurs in the surface. So and avalanche process in the bulk process. So M square FM term will be absent here. So that is same for pin and APD. And next is another noise is here, that is thermal noise or the Johnson noise. That is because of the dissipative circuit element like say resistance, etc. Those components are there. That times you have to consider the thermal noise. These times you see this thermal noise actually occurs. It occurs due to the thermal motion of the carriers in the circuit element. Generally, any circuit element is considered neutral over a certain length. But if you consider a small segment, some resistance, but if you consider a small segment within the small segment, because of the thermal motion of the carriers, charge gradient will result. So because of this charge gradient, positive negatives, some potential difference will be there, and because of this thing, some noise current will be generated. Right. So that is the thermal noise current. So thermal noise current, that is inversely proportional to the RLs. So that is because of the thermal motion of the carriers. I mean, and that is the Johnson noise, right? Thermal motion of the carriers. Right. Kb is the Boltzmann's constant, T the temperature, B the photoreactor bandwidth. So it is inversely proportional to the load resistance. This resistance can be minimized. This noise can be minimized by if you increase the load resistance, but still bandwidth also will be a factor, right? We'll see how bandwidth of photoreactor can be determined. That we'll see. It depends upon this capacitance value and the resistance value. We'll see it. So this, if you know all these noises and if you know the signal power, then you can calculate signal to noise ratio, that is IP square M square divided by these four noise currents, noise components. And for pin M square M FM, the FM with this will be, but for APD, M square factor will be there. And if you substitute these values here also, M FM, those factors will be there. And sometimes it is asked what's with the value of M so that you can have maximum signal to noise ratio. So in that case, you have to differentiate this Sn with respect to M and put equal to 0 and find out the value of M optimums. Right. So it is not too difficult. You can find out. So that is this after DSN. If you just consider it DSN by dm, and that put equal to 0. From that, you can find out the M optimum, that is 2qIL plus 4kBT by RL plus divided by xq into 1 into IP plus ID. I think x, that is this factor is there FM. We have, I told you this m to the power x. Some factor is there, is value, its value in between 0 to 1. So this is the optimal value of M for this to get the high signal to noise ratio, maximum signal to noise ratio in case of pin avalanche photoreactors. Okay, another factors that you have to consider while dealing with these photoreactors, that is the photocurrent and response times. You see this photocurrent and response times. The photocurrent, we have seen this whenever you see the to analyze the current in details, you have to consider again this pin photoreactor. And like it's a pin or a PD, you can consider it. Or let us consider pin photoreactor. And for simplicity, consider pin. And here, this is the this is the intrinsic regions of the depletion regions, P layer and N layers. And I told you the device is illuminated from the P side, and this P side is very thin, so that all the photons are absorbed in the depletion regions. Because we'll see it response times actually. If carriers are generated in these regions where the carriers are diffused and diffusion process slow process, so it will response speed will be less. So get high response speed, the carriers will be generated in the depletion regions. Actually, these carriers are the drift carriers. The carriers that are generated in the depletion regions are called the drift carriers. Drift carriers, right? So current due to these carriers called the drift current, and the of course, though it is very thin, still some carriers will be generated in the P side and N side. So P side, since it is connected to the negative supply, so you have to count electron diffusion. Hole diffusion will not be there, so electron diffusion will be there, and here also inside hole diffusion will be there, right? So the total current will be a drift current which are generated in the depletion regions plus diffusion current that are generated in the P layer and N layer. Of course, if you compare this hole diffusion current and electron diffusion current, generally electron diffusion current is very small because it is very, very thin. So hole diffusion current is the important factor that we have to consider. So now let us calculate how can you estimate this drift current and the diffusion current. In the if you consider the drift current, that means you have to consider the photons incident. So that is actually current density, that is photocurrent by area. So that is Q, that you can write it intensity. That depends upon the photon flux. That is the Q. We have seen it. This IP by Q equal to photon number of photons, number of carriers generated by number of photons. So IP by Q, so Q will be multiplied, and the photons you have to consider that is photon flux. Instead of this optical power, you can consider the photons. So that is phi 0 into 1 minus e to the power minus alpha SW. We have seen this power is absorbed exponentially within the device. So in terms of photon flux, we can write it Q phi 0 into 1 minus e to the power minus alpha SW. W is the depletion layer width. So phi 0 is the incident photon flux. So in this way, phi 0 also, of course, you can write it in terms of optical power that you have seen it. You see it here phi 0, that is P0, P by H nu, so P is incident power and by area. And this factor you have to consider, that is the reflection coefficient, because reflection coefficient. Reflection coefficient, because some of the powers will be reflected back. If you see it here, you see when the photon incident, not all the photons will be absorbed. Some photons will be reflected back in the same mediums. So you have to consider the transmitted part. If the R is the reflection coefficient, then 1 minus R will be the transmission coefficient, transmission factor. So that factor you have to multiply it. So that is the photon flux. Now, I told you the diffusion current will be due to electrons and due to holes. But since this is very thin, so you can neglect this electron diffusion current, but you have to consider the hole diffusion current precisely. So, so the hole diffusion current, it can be calculated like this in charge quantity equations. That is d2 Pn by dx2 plus Pn minus P0 by tau plus Gx equal to 0. If you solve this charge, this is actually, this is the number of carriers recombined. This is the number of carriers accumulated, right? Number of carriers because of the current, right? Number of the carriers. Accumulated number of carriers recombined, and also you see we have here in the chart you have to consider Gx, but Gx is the generation rate due to generation rate due to incidence of photons. Electron hole generation rate. This is the electron hole generation rate. Gx. So this Gx. So Gx actually you can consider if phi 0 photon flux. Actually, incident photon flux this one phi 0. You see, there is an incident photon, and so rate. If you just consider the times you have to consider the differentiate, you have to consider differentiations. So alpha factor will be there. Alpha factor will be there. That is the phi 0 alpha e to the power minus alpha x. So that is the generation rate, Gx. Right. So that is the generation rate due to photons. So in the charge control equations, these three factors will be there, right? And if you solve these equations, you can find out the PNs and with the initial conditions you see initial condition PN equal to PN0 when x equal to 0, PN equal to PN0, x equal to 0, and x equal to infinity, that PN equal to 0. So this two conditions, that is this is PN0 is the thermal equilibrium conditions. Thermal, I mean when there is no light. Still some because of thermally generated carriers will be there. So that is these ones. I mean concentrations at thermal equilibriums. So Pn equal to Pn0 when x equal to 0, but when x equal to infinity, then Pn equal to 0. So if you consider things, then you can solve this Pn. And once you know the value of Pn, you can find out the diffusion current. So that is, as per definition, you know, it is minus q dp, dpn upon dx. So if you know the Pn from these equations, from there you can find out the diffusion current. So once you get this diffusion current, then you can have the total current that you have seen it here, deep current plus diffusion current. So if you consider, I'm just writing the final expressions, the total current, so that J total, substituting these values, J total current, that will be Q phi 0, that is the drip current, Q phi 0 1 minus e to the power minus alpha s w by this 1 plus alpha s LP after simplification, these things will be there. These ones plus Q Pn0 dp by LP, the diffusion length. So right, here you can see these two terms are there. Two terms will be there if substitute value of drip current and diffusion current, solving this Pn0 and solving this Pn from these equations. So you get these two terms, and in these two terms, Pn0, you see this is very small. So you can neglect these terms. So the total current generated will be determined by this, the incident photon flux, the total current. So this is the photocurrent in case of the photodetectors. Right. This is shown for pin photodetector for simplicity. But in this way, similar way you can calculate the photocurrent in case of photodiode. So the current basically consists of the two components: the drip current and the diffusion current. Drip current due to the carriers that are generated in the depletion regions, and diffusion current due to the carriers that are generated in the P regions and in the N regions. But P regions is very thin, that's why electron diffusion we neglected, and only hole diffusions are considered. Okay. Next, you see the response times. Response times is another factor that you have to consider while dealing with the photo detectors. The response times, it depends upon these three factors. You see it here. One is transit time of the carriers in the depletion regions. Next is the diffusion time of the carriers that are generated outside the depletion regions. We have seen this carriers can be generated in the P region and N regions. So there is a diffusion time constant. And also it depends upon the capacitive effect of the photodiode, that is RC time constant photodiode. Okay, one by one, if you just see it, say transit times of the photocarriers, you can calculate this if you know the drift velocity and the depletion layer width, then you can find out the transit times, right? So TD, that is W by VD. So if you know the drift velocity of electrons and holes, that is generally 18 to 10 to the power 6 for electron, it is 8.4. 8.4 into the power 6, and whole it is 4.4 into 10 to the power 6 centimeter per second. Centimeter per second. So if you know the carrier velocity, you can find out the transit time of the carriers, right? Of course, it depends upon this, the field strength also. Typically, if the field strength channel, it is 2 into 10 to the power fold. Field strength, that is field strength, generally it is 2 into 10 to the power 4 volt per centimeter, right? So generally it is for the silicon photodiode, this transit times, I mean response times, it is around 0.1 nanosecond. Anyway, you can calculate in this way the transit times of the carriers that will contribute to the response times. Another factor is the diffusion time of the carriers. Well, I told you diffusion process is a slow process. So aim should be, while designing the photoreactors, aim should be to design the photo in such a way that all the photons are absorbed in the depletion layer. And in fact, the response times, if you see in the response times, it is determined by the rise time and fall times of the rise time and fall times of the photodiode, right, of the detector output. If you some step input, if you apply the step, you see step response. From the step response of the optical radiance, the response times of the photodetector can be determined. So in this context, rise time, fall time is here. So rise time means it is the 10% to 90%, 90% of the output pulse, and fall times it is just reverse 90% to 10%. So for if the depletion layer is fully ideally, if the depletion layer is fully depleted of free carriers, if I mean for large reverse bias, if you apply large reverse bias, then I told you the depletion layers will be the depletion layers will be free of mobile carriers. So in that case, rise time, fall time will be equals. Tau R will be equal to tau F. But generally for low practically also, and for low reverse bias also, some carriers will be present. So in that case, they are not equal. Rise time, fall times are not equals, right? In fact, if you see the charge carriers that are generated in the depletion regions, they will be collected quickly. But if the carriers generated in the P layer and N layers, then they will diffuse slowly to the depletion regions. There and then they will be separated and will be collected. So right. So that means the response times is determined by the slow carriers as well as fast carriers, because you cannot avoid the carrier generated in the P layer and N layers. But if you see the output response, then The fast carriers, that means the drift carriers, they determine the 50% of the output within a very short time intervals. You see, this curve is time versus output response, total output in percentage, right? So if you see it here, 50%, this is the curve, right? Output versus the times. So 50% of the output, if you see 50% of the output, it is determined by the fast carriers. That is within a very short time intervals, maybe less than 5 nanoseconds, right? But the remaining 50%, it is determined by the slow carriers. This is determined by the slow carriers and over a longer times. This is the slow carriers over a longer period of times. I mean, they will provide long delay before the output reaches to the maximum value. You see that. You see it, they provide the longer delay. So that is a case. So if you consider these things from this response time point of view, so your aim should be like that. All the carriers will be generated in the maximum carriers can be generated in the depletion layers. So can be generated in the depletion layers, not in the depletion, not in the P layers or N layers. Also, you see, response time depends upon the depletion layer width and the capacitance. So if you see, generally we have seen this quantum efficiency can be increased. If you see here, quantum efficiency can be increased if more photons are incident and the more carriers are generated, right? But if it is very large, then carriers will take longer times to cross it, so speed will be less. Depletion layer should be such that you can have high quantum efficiency as well as fast response speed. So generally it is it is greater than this 1 by alpha s. Depletion layer width, it is greater than the inverse of the absorption coefficient, so that the most of the light is absorbed, right? So if you have, suppose if the step response is here, if the depletion layer is quite large and capacitance effect is small, then almost same response you are getting it, right? But if the depletion layer is large, you see depletion layer width is large, that is 1 by alpha s, but capacitance is large. Well, capacitance, photodiode capacitance is large, then you see large CG capacitance, Johnson capacitance, then this you see it is very much distorted. It is very much distorted, right? And you see Johnson capacitance is determined by this dielectric constant of the photodiode materials, the depletion layer area and depletion layer width. So the junction capacitance will increase if W is very thin. W is very thin, then junction capacitance will be quite large. So junction capacitance if large means you see it is much distorted. Right. So capacitance should be small, and depletion layer or width also you see it should be greater than 1 by alpha s. So one typical value is, you can see it here, where slow and fast carriers, how they determine the, see it here, this curve. Here very thin depletion layers, and W less than here W less than less than equal to 1 by alpha s, effective absorption coefficient, and capacitance value is small. Then the, I mean, if the depletion layer is very thin, then you see, then also carriers will not be collected. Again, they will diffuse back into the depletion regions, right? So these things are there. So that's why you see it here. One typical example is shown here. Where depletion layer is thin and capacity is small. Then you see some tail is here. If you see carefully here, this portion is determined by the fast carriers. This portion determined by the slow carriers. But during fall times, this portion is determined by the fast carriers and the drift carriers. The longer tail is here. That is because of the diffusion carriers. So some anomalies are there. If W is thin, as well as capacitance is very small. So some if W thin means, why W thin it is distorted? That because W thin means junction capacitance will be quite large. You see, W thin means junction capacitance will be quite large. So there must be a trade-off between this depletion layer and the response speed. And generally, depletion layer, I mean, so excessive RC time constant also, if capacitance is very large, then RC time constant will be quite large. So that will limit the response times. So some compromise will be there between high frequency response and the high quantum efficiency. And in that case, the depletion layer width, generally it will be in between 1 by alpha s and 2 by alpha s. Right? It should be in between these things. So that is generally considered to increase the response speed and high quantum efficiency. So this condition is there, right? These are the conditions. If depletion layer is very large, then quantum efficiency will be high, but at the same time, response speed will be less. If depletion layer is very thin, then capacitance value will be quite large. Then also the very much distortion will be there. So the depletion layer will be in between 1 by alpha s to 2 by alpha s. Alpha is the effective absorption coefficient. Another thing is, yes, I told you, all the noise currents depends upon the photocurrent. All the depends upon this bandwidth, photodetector bandwidth B. You can see all the photocurrents. We have seen it. Photocurrents is the photodetector bandwidth is B. So how can you determine B? I told you it's a combination of this peak determined by the capacitance, total capacitance value, total resistance value. In fact, this circuit can be considered low pass RC circuit, and from the 3 dB you can find out the bandwidth. So the bandwidth, that is actually the parallel combination of the resistance and the parallel combination of the capacitance. So that is actually 1 by 2 pi RTCT, right? Pass band you can find out from the circuit. So if you that consider the low pass filter, then from the circuit, this we can determine the pass band. Well, another thing is this photodetector materials. You see, photodetector materials is another factor. And generally, photodetector materials should be chosen in such a way it should provide high sensitivity, high responsivity, as well as high quantum efficiency. And that condition will be these two things we can achieve if photon energy it is greater than equal to band gap energy. Also, there must be low dark current. Then only you can have best responsivity as well as high quantum efficiency. So what are the materials? Materials can be silicon, germanium, gallium arsenide, indium gallium arsenide, indium gallium arsenide phosphide, etc. Generally, photoable regions, silicon is preferable because silicon bandwidth is 1.17 electron volt. So if you calculate the cutoff wavelength for silicon, it is 1.24 upon Eg. So that comes 1.06, right, from these regions, microns. Other than silicons, materials used like gallium arsenide is here, right? Gallium arsenide most probably gallium, antimonite, those things are there. Gallium, antimonite, those are also there, right? And in the longer wavelength side, you see the materials that are considered indium gallium arsenide. This longer wavelength side, 1.0 to 1.6, indium gallium arsenide is used. In that case, here the advantage of these things, you can vary the band gaps. So it can cover up to 1.65 micron, 1 to 1.65 microns, right? And you see, substitution coefficient is quite large for this in the long wavelength for these materials. Of course, germanium protector also is full for longer wavelength side. Of course, up to 1.55 micron, germanium photodetectors is used. But there are some certain drawbacks of germanium photodetector is here. Here, dark current is very high, quickly because of its smaller band gap. Band gap of germanium is generally 0.66, like these things, 0.81 volt. So, because the smaller band gap, easily electrons can there will transfer electron from valence band to the conduction band. That will result the dark current. So dark current is high, right? Also, it has high excess noise factor. I mean, if it is used as a avalanche photoroute, then these the carrier ionization rate is small. I mean, that is whole ionization rate by electron ionization rate. The ratio is small, right? So because of these things, generally 3,5 compound semiconductors are preferable. Right. Of course, germanium photodetectors have also been used for these high data transmission experiments over longer distance. Right, germanium photodetectors. And apart from these germanium photodetectors, you see other materials are used like indium gallium arsenide, indium gallium arsenide phosphide. These are also useful. Because these detectors have high contact efficiency, fast response speed, and low dark current, right? And also they will have a large difference of electron ionization rate and hole ionization rate. Of course, silicon has the largest difference of the ionization rate. Thus, silicon is widely used for the short orbital regions, short orbital regions, right? But the advantage of this 3,5 compound semiconductor is this: here you can vary the band gap, so wide response you can have it, wide spectral response you can have it. Anyway, so these things are there already I mentioned. We'll see next times the optical receiver. Optical receiver that can be digital optical receiver, can be analog receiver. Digital case, the bit error rate can be considered. I mean average error probability. But considered for analog case, it is signal to noise ratio is considered. Next time we'll see it. The receiver, how you can determine the performance of optical receiver in case of digital one and in case of analog one. Analog one, just we have seen it is similar to that. Digital case, we'll see how the performance can be evaluated based on some transfer functions. Right, that we'll see next times. किसी का कोई क्वेश्चन है तो पूछो, जितना डिस्कस किए. किसी कोई क्वेश्चन है तो पूछो. Anybody, if you have any questions?
No, sir.
Okay, then.